Well, once again, it's the physics video lecture. Physics 105B video lecture 25. So let's begin. We're talking about moments of inertia, inertial tensors, and we're going to do a little bit of an integration discussion before we go back to the actual dynamics. And so we'll do some integration theory as discussed last time. So first of all, the inertial tensor, just so we have it in front of us, I sub ij, we got integral dm, and then r squared delta ij minus xi xj, so we're integrating over the body, and the dm would be the density d volume. I want to write it that way. Density times d volume. Density, of course, doesn't have to be uniform. We're typically talking about a uniform density. So this time we want to integrate some of these things up with curvilinear coordinates. And we already saw if we have a symmetric body, there are only going to be diagonal elements. And they have each diagonal element has the original meaning of the moment of inertia with respect to the corresponding principal axis. So things are looking good in that regard. Let's return to some basic bodies, and then I'll show what we want to go from there. So let's go just for the I sub disk. Uniform disk. Disk of radius r. And this time we're going to use dm x squared plus y squared. This time we're going to use the plane polar coordinates, because then we're going to do the sphere, and with the sphere we want to use the spherical polar coordinates. Okay, so getting started with the plane polar coordinates, we have for our dm, we have mass over pi radius squared, and then we have, since we're using plane polar coordinates, well, let's go ahead and do it in an extra step. dv x squared plus y squared. Okay, but now I'm going to go ahead and write plane polar here. And we can pull out the density, m over pi radius squared. And then it's going to be a double integral. We know that we have r dr d phi, so dr from 0 to capital R, d phi from 0 to 2 pi, since we're doing plane polar. And then we've got so that's taking care of this, and then we've got the x squared plus y squared, which of course is just the r squared. R squared, so we have m over pi radius squared, and then we have the d phi integration is going to give us 2 pi, and then we're going to have r cubed, so we're going to have integral of that is r to the 4th over 4. So I can, in this case, I can just make short work of it. We have r to the 4th divided by 4, and that's going to be an m. The pi's cancel, r squared, so it's going to be m over 2 r squared. Okay, that's how we do that with plane polar coordinates. I'm going to put a question under here. Since this was the disk, question, suppose we wanted to do the elliptical, and by the way, this is the disk or the cylinder, right? Disk or cylinder. But now the question is, what if we had a lamina, a planar object with the cross section of an ellipse? So what about an elliptical cross section? So instead of x squared plus y squared less than or equal to 1, or, yeah, for a unit circle, we would have x squared over a squared plus y squared over b squared less than or equal to 1, right? This would be the unit circle, this would be the ellipse. Unit circle, we would have just had m over 2 here times r equals 1 squared. So the elliptical cross-section, it turns out we're going to be able to make a transformation from plane polar coordinates, from integral over plane polar coordinates, that will transform the unit circle onto the ellipse. So ellipse. Okay, so that's what we're going to do. The next one along these lines is the moment of inertia of the uniform sphere. So next, I of a sphere of radius r. Okay, well, we've probably seen this in the past, that it's 2/5 mr squared. So we want to generate that using spherical polar coordinates. So using spherical polar coordinates, we'll start with our dm x squared plus y squared. And for the dm, we're going to have integral mass over volume. So there's our density. And then we'll have a dv and an x squared plus y squared. Well, I should draw my picture here. X, y, z, and we're imagining that we're rotating about the z-axis for this one. Okay. So how do we do that in spherical polar coordinates? Well, there we can pull the m over 4/3 pi radius cubed out, and we need the volume, the triple integral over spherical polar coordinates. So there we know, or we can look it up, but part of our project is going to be to derive all these things. In other words, the r dr d phi, sure, we know it or we've looked it up, but I'm going to give it more general formula for finding these things. Here we have the r squared sine theta, dr d theta d phi, that's the volume element. And then the x squared plus y squared, we have to remember what our x and y are in spherical polar coordinates. We have r sine theta cos phi squared plus r sine theta sine phi squared. And I'm going to take it one more step and let you guys do the very end of it. It's actually no big deal at all. In fact, we can see here we're going to have an r squared, and then we're going to have cosine squared phi plus sine squared phi. That's going to give us a 1. So this is actually just r squared sine squared theta. Actually, we can write this down. So we've got m over 4/3 pi radius cubed. That was the density. Yeah, I didn't write the limits, but we'll get them right here. Then we have r squared sine squared. We have another r squared sine. So we actually have r to the 4th sine cubed theta. We've got dr d theta d phi. d phi is 0 to 2 pi. The d theta is 0 to pi for a sphere, and the dr is 0 to capital R. So when you do that, as long as we haven't made any mistakes, I don't think we have. The d phi immediately gives you 2 pi, it's going to cancel that. The dr is going to just give you r to the 5th over 5, and that'll cancel those. You'll have your mr squared, so the dimensions are of course right. And then you have to integrate the sine cubed of theta. And one thing you can do is write 1 minus cosine squared theta for sine squared and then sine theta, and integrate those two up, and they go pretty quickly. So when you do this, you actually do get your 2/5 mr squared, which is nice. You know, here's the thing. Maybe just leave enough room in your notes and then fill this in. It's a good little calculation, as opposed to saying do it for homework. Okay. But yeah, you definitely want to fill this in and know how this goes. It's just 2 more steps, and sine cubed theta this here. Okay, so again, the question that goes with this one, okay, so I've got a little space, I'll use this right here, is what if instead of a sphere we had an ellipsoid? So this was the question that went with our disk. This is the question that goes with our sphere. Suppose we have a uniform ellipsoid, question mark. You have a uniform ellipsoid, we're looking at x squared over a squared plus y squared over b squared plus z squared over c squared less than or equal to 1. Right, that's our area that we're integrating over. And as opposed to, you know, a, b, c equal 1, that would be the unit sphere. So is there a way to transform the unit sphere onto the ellipsoid? And of course there is, and you just have to extend your x and your y and your z in terms of a, b, and c. So transform unit sphere onto the ellipsoid. Well, the ellipsoid really is an important shape for rigid body motion, because our planets and celestial bodies, if they're rotating, they tend to be what's called an oblate spheroid. And that's also known as a symmetrical top, where 2 of the moments of inertia are the same and the third one is different. So for that reason, we want to actually get the inertial tensor of the ellipsoid. Okay. And that's our project, so that will be a homework problem, but it's going to take some setting up, because I want to talk about some integration theory in general, because then we can generate these expressions here, these volume elements that we've already talked about, volume elements, and so forth. So good. I'll just put this as a heading. And then we'll do a bit of this integration discussion. So yeah, our technique for integrating is going to be transforming one of these objects onto the other. Like unit circle onto an ellipse, unit sphere onto an ellipsoid, and then we'll be able to get these integrations. Yeah. So this is integration the transformation formula. And And what this is a generalization of of our fundamental theorem of calculus when we do U substitution. So let's see here. Transformation formula, I'll start with this integral here. F of U of x, U prime of x, dx from A to B. Okay. So what is that equal to? Okay. That's equal to integral F of U du from U of A to U of B. And the way we can, of course, show that is if we have an antiderivative of F here, okay, let F be the antiderivative of lowercase f, then what we're looking at over here is d dx f of u of x dx is equal to f of x, right? It's the antiderivative, inner derivative u prime of x dx. So it's a to b. It's a to b. But since that's an antiderivative, we can also say that this is equal to, I got this in the right order? Doesn't matter. So this is equal to f of u of b minus f of u of a. Yeah, antiderivative. And that is, of course, equal to that. So that's just how we do U substitution. What I'm going to draw our attention to now is that this generalizes to n dimensions, okay, to n-dimensional integrals. So next, generalization to integrals in n dimensions. And let's see what we first define. So this is actually a coordinate transformation, okay, going from U and then going from X to U. So this is a coordinate transformation. And so I'm going to write down a more general coordinate transformation. And by the way, the plane polars and the spherical polars are, of course, also coordinate transformations. Those will be our good examples. So let's see, we got some nomenclature here that we're going to have to. Yeah. Okay, so let phi, I'll call it vector of C vector, be a coordinate transformation, and I'll write it out So we're going for n variables right away. So we're going for n. Let's go ahead and get rid of this. phi sub 1 is equal to phi sub 1, c sub 1 all the way to n, and all the way down to phi sub n is a function of c1, c sub n. Okay. So if that's a coordinate transformation, what am I talking about? Let's do, before we define any more, example plane polar. Then you know I have x equals r cos phi and y equals r sine phi. So my r and phi are these variables c sub 1 to c sub n, and my phi 1 to phi n are my x and y. Okay. So good. So that's an example. Next, we have to define the Jacobian here. So next, let d phi ij be equal to d phi sub I d c sub j. Okay. And that's the Jacobian matrix. And see, in my own notes, I actually have this. Oh, see, like that. I'm not going to put a vector on the phi. Okay. Yeah. This is the Jacobian matrix. And determinant determinant of this is equal to the determinant of this matrix d phi d c sub j. Then we get the following transformation formula. And I'll have to define some stuff. So we're going to have an f of phi of c, and then the absolute value determinant d phi c, and that's an n-dimensional integral dn c. J is the board filler equals integral f of y dny. So if this is, I'm going to call this capital U, this is a region of n space, and this is its mapping, phi of U. Okay. So this is the domain. Okay, and the domain gets transformed right here. So this is actually, to the letters that are a little bit different, the n-dimensional version of our standard U substitution. And what this Jacobian matrix does, its determinant gives us the volume element. So put this in a box and do a couple of applications just to make sure we see what's going on, because there are a number of different coordinate systems that one can use this with. Of course, you've got your Cartesians, your plane polar, your spherical polar, your cylindrical, and then other coordinates, parabolic and other type of coordinates as well, where you transform your integrals in this way. Now we of course have to go for the plane polar to make sure we see what's going on here. So the example with the plane polar coordinates, in order to generate the integration that we just did, so we have the x, and I'm going to call it phi sub 1 in honor of these new letters here. Yeah, I will. So we have our phi sub 1 and our phi sub 2. We're using those letters of r and phi. Those are our x and y. We have r cos phi, r sin phi. You know, I could call these c sub 1 and c sub 2, but we're going to stick with this, okay? So, how about this d phi ij that we're talking about right here? Okay, so the d phi sub I, d c sub j, d phi, let's call that the matrix. So d phi sub 1 dr, that gives us cos phi. D phi sub 1 d phi gives us minus r sin phi. D phi sub 2, right, I'm doing the 2, 1, so d phi sub 2 dr is equal to sine of phi. D phi sub 2 d phi is r cos phi. So that's that transformation matrix. And of course, its determinant, r cosine squared phi minus negative, so plus r sine squared phi. So it's just equal to r. I'll squeeze that in right here. And determinant of d phi is simply equal to r. So yeah, make sure you see that, how I did this. This was the 1, 1, 1, 2, 2, 1, 2, 2 component of a 2 by 2 matrix. So when we have that, so right underneath this integral here, I'll get rid of this now. Right underneath this integral here, we could now say we have integral f of r and theta, okay, or I'm sorry, r and phi, and then we have the determinant of this, which is r, and then we have the d squared c is dr d phi. So that's how that comes about. So this is actually the volume transformation, just r right here. R dr d phi. Good. R cos phi, r sin phi. And that would be equal to, I'll go ahead and put double integral here. That would be f of x and y dx dy. So that's what we have in this transformation formula. The determinant, which we just took, gave us this. And now what about the domains? Okay. So the domains transform with the as well. So if we're doing all of space, the dr would go from 0 to infinity, and the d phi would go from 0 to 2 pi. And here we would have minus infinity to plus infinity, minus infinity to plus infinity. But what if we had the unit circle? If we had the unit circle, we'd be going 0 to 2 pi and just 0 to 1 in the r. And here, it'd be a little more complicated, in fact. We could just write unit circle here and figure it out. So good, the transformation, and this I will put as homework. Use spherical polar coordinates or calculate the Jacobian matrix and then its determinant for spherical polar coordinates. Jacobian matrix and its determinant so good. Calculate the Jacobian matrix and its determinant for spherical polar coordinates. I'll get started on it. Okay. So it's the same as what we had with the plane polars. We're going to do a little more work. So again, for the spherical polars, we have phi1, phi2, and phi3. But those are just fancy names for x, y, and z, okay? R, theta, and phi. R, theta, phi. And of course, those are R sine theta cos phi, R sine theta sine phi, and R cos theta. So we're familiar with those. Now we have to get this 3 by 3 matrix, so I'm just going to call it d phi ij, show that it's a matrix. Let's fill in a couple of these. So the coordinates 1, 2, and 3 are r, theta, and phi, because that's the order I drew them in right here. So d phi 1 dr, we get sine theta cos phi. D phi 1 d theta, we get r cos theta cos phi. Guess you need a bigger matrix here. D phi 1 d lowercase phi is minus r sine theta cos phi. And then you go through here as well with respect to r, sine theta, sine phi, etc. I'm not going to write them all out. Sine theta, sine phi, etc. So you have that 3 by 3 matrix. You have to take its determinant, and then you're going to find out that the determinant, we hope, show that, show that the determinant of this thing is r squared sine theta. And it's not quite that bad because there are some zeros in it, so for when you expand it out. But yeah, that's where that volume element comes from. And then if you do a spherical polar coordinate version of this, you've got, your transformation, you've got r squared sine theta dr d theta d phi. Okay, so far for the transformation formula, and it's important to note that your domain here, this domain is, a subset of some, r to the n. This domain maps onto what that transformation maps it onto. Okay, so you have a certain domain here, then the transformation into, x, y, x and y maps it on. Okay. So anyway, this symbol here is the mapping of that domain. Good, so this will be good. Now what we want to do with this, let me check the time first. We want to do those transformations for our ellipses and ellipsoids. Actually, I'm going to leave that up there because that has the formalism. Good. So now we'll do the ellipse. And the ellipsoid. So my next example is I just want to find the area of an ellipse. Using the transformation formula. So we know we have x squared over a squared would be in x and y we have a and minus a minus b and b, x squared over a squared, y squared over b squared less than or equal to 1. So that's the ellipse. We need a transformation of the unit circle onto the ellipse. Phi of c and eta equals Phi1, Phi2 of c and eta equals a times c and b times eta. This transforms the unit circle onto the ellipse. Circle onto the ellipse. How does it do that? Okay. Eta is an element of the unit circle, then we have c squared plus eta squared is less than or equal to 1. So element of the unit circle less or equal to 1. And this transformation here, Phi1 squared over a squared plus Phi2 squared over b squared is equal to a c a squared plus b eta squared over b squared. Of course, the a and b's cancels here, equals c squared plus eta squared is less or equal to 1. Okay. But this, of course, is the ellipse. So now we want to look at the integration formula. Good. So now, I wanted to have everything on the board, but you can never have everything on the board. But we'll do the Jacobian over here. So now we need to do this formula. We have the Jacobian matrix. Let's call it D Phi ij. There's our transformation. D Phi1 dc, the first variable, is just a. D Phi1 respect to eta is 0. There's no explicit eta there. And second row we get 0 and b. And of course the determinant of this really is equal to a times b. So good. Actually, we can have it all on the board at once. Now we're going to go ahead and write this thing down here. The function f in this case, since we're just looking for the area, is just 1. Okay, we're just looking for the area. So here we have here for the unit circle, which is what we're integrating over here. The determinant, okay, so this is this formula right here. So I'm just going to write, we've got a 1 for that, and we've got AB. I can put it into absolute values just to make sure we see that. AB, and then we have AC d eta is equal to, I can write dx dy for the ellipse. So the unit circle here, ellipse here. Yeah, transforms the unit circle onto the ellipse. And here it's actually, we're actually looking at it now, right? Again, the function is just 1 because we're just doing the area. And this integration here, make sure I'm not leaving any nomenclature out. Now we're good. Yeah. So right here, we pull out the AB, and then the integral over a unit circle, it's just pi, right? Pi r squared, or just pi for the unit circle. And over here, we're saying we're integrating dx dy over the ellipse, right? Up there. So this is area of the ellipse. Area of the ellipse. And that's how the transformation functioned. Now, I'm going to assign a couple of things. Namely, now that we've done this, you can do the same construction for the volume of an ellipsoid and compare it to the volume of a sphere. Okay. So I'll put this on the homework as well. This will be interesting. And the transformation is going to be the same. Let me even describe it before I go on. So if we want to do the same thing for a volume of an ellipsoid, okay, x squared over a squared, y squared, b squared, z squared over c squared less than or equal to 1, then our transformation will be a times c, b times eta, c times zeta, right? We'll just have that a 3-component vector instead of 2. And then we'll have this same thing for the ellipsoid compared to the unit sphere. So actually everything's going to go exactly the same. It'll just give you a chance to work through the problem. So we got the area of an ellipse. So homework, perfect with this board because the generalization should be really clear. Generalize this to obtain volume of the ellipsoid. Okay. And yeah, it's so direct that we know that the volume of the sphere is 4/3 pi r cubed, right? And the volume of the unit sphere is going to be 4/3 pi, and then the volume of the ellipsoid is going to be 4/3 pi ABC. Okay. So do that. That will just be a good exercise. That's as much as we're going to do today. So I'll tell you what's next. So with this transformation formula, and these are just fancy letters for coordinate transformation, we can always get those volume elements. And there are other sets of coordinates out there that you can end up using this for as well, but we're just going to use, you know, cylindrical, plane polar, spherical polar. So yeah, you generalize this and you get your volume and you see how that works. Now the more challenging thing is to get the moments of inertia, and you have to do the same thing, but now your function is no longer just one. You know, there's your x squared plus y squared set of coordinates there, and you have to, you know, you have to monkey around with it a little bit, but it's interesting as well. So that's what we're going to do, and I'll set those up. I may just even do them. But we're going to use this transformation formula to get the moments of inertia of the ellipse and the ellipsoid. Okay. And they're important, and this is a nice little section of mathematics. I actually also have a little proof, okay, not the full mathematician's proof, but a semi-proof for this formula, which is actually pretty interesting too. I may do that next time. Because you want to see how this thing is related to a volume. Okay, that's kind of important to see how the determinant is related to a volume. And it is. So good, we can do that as well, but that's where we're headed. So we'll do another hour of talking about these moments of inertia, inertial tensors for ellipses and ellipsoids, and in general. And then we'll go back to the dynamics that we were talking about. Okay, good. See you guys next time.